Somewhere far out in deep space sits an object so incredibly massive that its immense gravity captures light itself. Because none of that light can escape, we can't look inside to see what's actually there. The interior remains hidden from all human observation. To bypass that physical limit and figure out what lies in the dark, we have to rely on math and take a theoretical journey inward. Probing this mystery requires an examination of the rules of physical reality and identifies the specific moments where those rules appear to fail. Despite the name, a black hole is a highly compressed physical object left over from the death of a massive star. When the star burns through all of its fuel, the outward pressure stops. Its own gravity immediately takes over, crushing all of its matter inward into an impossibly small volume. To picture this level of density, imagine taking the entire mass of the Earth and squeezing it down until it's the size of a glass marble.
Packing so much matter into such a tiny space generates a gravitational pull so intense that escaping it becomes mathematically impossible. Our journey inward starts at the black hole's outer boundary, an invisible threshold in space called the event horizon. What we actually see from the outside is the accretion disk, clouds of spiraling dust and gas gathering right at the edge of the void. This material accelerates to incredible speeds, much like water accelerating as it spirals down a drain. The event horizon marks a strict physical limit. Once anything crosses that line, turning back would require moving faster than the speed of light, which is physically impossible. It acts as a one-way cosmic curtain, hiding the physics occurring on the other side. To see what happens past that curtain, imagine an astronaut physically falling across the event horizon. Almost immediately, they would experience differential gravity. The force pulling on their feet would be astronomically stronger than the force pulling on their head. This extreme difference stretches the body into a continuous thin string. Scientists have a remarkably literal term for this: spaghettification. This destruction happens well before the astronaut ever reaches the center, proving that human exploration of the interior must remain theoretical. If we follow the equations past the stretching effect, we eventually arrive at the absolute center of the black hole. This is the singularity. It is a single, microscopic point where all the original star's matter has been crushed down to a size of 0. Because you are dividing a massive amount of weight by 0 volume, you get a point of infinite density. This state breaks the mathematical equations we use to describe the rest of the universe. At this coordinate, the fundamental concepts of space and time as humans understand them cease to exist. We only know this limit exists because of Albert Einstein. His equations of general relativity were the first to predict that gravity could bend space to this breaking point. The singularity isn't a traditional place you can visit, but rather the boundary where current human science and physics fail. The laws of physics create a trap here. Because information cannot travel faster than the speed of light, whatever happens at the singularity can never be broadcast back to the outside universe. The black hole locks away the data of its interior, keeping its secrets permanently hidden. But returning our focus to the wider galaxy, this mystery doesn't stop researchers from actively studying these objects. Astronomers can track how a black hole's gravity slingshots nearby stars and measure how it bends the light from distant galaxies. Through these indirect observations, we have gathered more data on black holes in the last 10 years than we did in the previous 100. Rather than a scientific dead end, the impenetrable center of the black hole remains a catalyst, requiring researchers to develop more precise theories of how our universe functions.